everybody. Today we are discussing the next topic, that is chiral auxiliary controlled asymmetric synthesis. So in the last class we discussed the asymmetric synthesis by using enantiomerically pure compound. And next is the chiral auxiliary controlled asymmetric synthesis. So in the chiral auxiliary asymmetric synthesis, we are connecting an enantiomerically pure compound to a starting material, and this enantiomerically pure compound is known as the chiral auxiliary, and which is attached to the starting material, and which does not involve in the chemical reaction, but it produces a hindrance to the attack of the nucleophile. So the nucleophile can choose only one direction for the attack, and the reaction is a diastereoselective reaction, and this is mainly due to the already one enantiomerically pure compound is attached to the starting material, and we know that every enantiomerically pure compound have a configuration. So the one of the configuration is fixed in the product, and we are generating the new chiral center in the starting material. So that's why this type of the reaction, as we said in the earlier, it is a diastereoselective reaction. And after the asymmetric synthesis, we can remove the chiral auxiliary, and chiral auxiliary can be recycled. An example is the hydrolysis. Now, this is the schematic representation of the action of the chiral auxiliary. Here, we are using the propionic acid as the starting material. We know that there is no chiral center is present in the starting material, and we are connecting the starting material with a chiral auxiliary, and it is shown by the red ball. And after the chemical reaction, we can see that a asymmetric chiral center is generated, and the chiral auxiliary is removed, and the product is regenerated. The starting material is regenerated. Here we can see that the starting material is propionic acid, and the final product is an enantiomer, and here we can see that a chiral center, and one of the substituent is NH2, the other is CH3, and the next substituent is hydrogen, and the last one is COH. So a new chiral center is generated. Already the starting material have a chiral center which is coming from the chiral auxiliary. After the asymmetric synthesis, a new chiral center is generated in the starting material, and we can remove the chiral auxiliary. Thus chiral auxiliary can be regenerated just like our catalyst, and the starting material also produced again. Now, Prolong's rule. Prolong's rule means, last we discussed the Cram's model. Stereogenic center is here in the Cram's model. Stereogenic center, that is carbonyl group, is alpha to the carbonyl group. That means the chiral carbon atom is attached to the alpha position of the carbonyl group. But there are some examples in which the chiral center is quite far away from the reaction center. So in which two carbons, carbonyl carbon, one is in the ester carbon. So these type of one of the example for the carbonyl group which is quite away from the reaction center is alpha keto acid. So in the alpha keto acid, we know that the carbonyl group is far away from the reaction center, and we are adding the Grignard reagent, and the addition is always taking place through the smallest group, and here the newly generated chiral center is in the fourth position. That's why the Prolong's rule is an example for the induction of the asymmetric center in the fourth position, and this reaction is known as 1 for asymmetric induction. Now we are moving into the example. This is the example for the Prolong's rule. As we discussed earlier, in the Prolong's rule, the reaction center is shown by the green arrow, and which is connected to an ester group, and the reaction center, that is carbonyl group, is far away from the chiral center. Here I can see I shown the chiral center as